Okay, hello everyone. Welcome to our last big group meeting today. So we have three presenters. That is Arian, Nani, and Renbeck. So Arian, would you like to start first?
Yeah, I can go first.
Okay.
You guys see it?
Yeah.
Okay, so I'm going to be talking about two topics. One is application of deep reinforcement learning, and the other is learning from multiple tasks or multitask learning. I'm going to start with deep reinforcement learning. So, deep reinforcement learning is kind of data inefficient because it requires a lot of data and a lot of iterations to go through the data to give results for even simple tasks. So, to circumvent this, a lot of uh, companies or like researchers who use this method use simulated environments first to get some data and then feed it into the DRL models to train them. But because there's a lot of gap between what simulated data can give you and what real environments give you, uh, the model is difficult to operate feasibly. So that's why you'll usually see DRL being used in closed environments like video games and stuff. A lot of companies that do use this use like deep learning platforms, which are like platforms with a large amount of data already on them. So that helps. Um, I've used three examples of DRL in real world environments: robotics, healthcare applications, and in chemistry. So, starting off with robotics. Um, Robotics uses DRL frequently now because ever since Google published its soft actor critic algorithm, a lot of robotics researchers have been using it in their studies. This algorithm helps robots use reinforcement learning to learn real world tasks without the need for huge data sets. And it at the same time safeguards the robot from doing something that could damage it because that happens a lot in robotics research. So, a real like case of this was when researchers trained an insect robot to walk in just a few hours and a robot hand to carry out simple tasks using deep reinforcement learning. In healthcare applications, uh, there's already a large amount of historical medical data, so the availability of data is not really a problem. And we use DRL in like healthcare to evaluate the success of treatments. So, for example, it's used to predict drug doses for patients and to find optimal drug dose cycles in chemotherapy and to select treatment regimes, like combining all these different medications based on existing data. In chemistry, DRL has been used to optimize chemical reactions in the lab, and DRL has already outperformed an existing state of the art algorithm. And they did this by at every step it predicted the what action would generate the most desirable reaction in the experiment. The next topic is multitask learning, learning from multiple tasks. In multitask learning, the main goal is to try to have one neural network do several things at the same time. So, in the same neural network, we do a lot of tasks, and each of the tasks help execute the other tasks. In transfer learning, we it's closely related to transfer learning because in transfer learning we do things in a sequential way where the data and the stuff from the previous task helps the next one. In this, we execute a lot of things simultaneously, so everything kind of helps each other. I've used an example of a self-driving car for this. It's also used in computer vision, but self-driving cars also use it. So it's obvious that a self-driving car would need to detect a lot of stuff to see where it needs to go. So stuff like pedestrians, stop signs, other cars in the way, traffic lights. So when you feed an input image into a multitask learning algorithm, it would give you a vector yi of dimension 4 by 1, because you have four things you need to detect. And then, so because of that, our training data labels would be of dimension 4 by n. If we don't do this, if we use the neural network for just detecting one thing, our data training data labels would be 1 by n dimension. Here we have 4 by n. Um, so using this, we can feed it into the neural network, and we can then use this to predict uh, what else we want. There are a few cases where there are some cases where multitask learning makes a lot of sense. So cases like when you're training on a set of tasks that could benefit from having shared low level features. So for example, in the car, like in the self-driving car example, uh, recognizing traffic lights, cars, and pedestrians should have similar features that could help it recognize stop signs. So object recognition is not, it has a lot of similar low level features. So in this case, of course, multitask learning makes sense. The amount of data you have for each task is similar. For example, we had like four tasks in the self-driving example. You can have, suppose you have 100 examples of each of the tasks. So now when the learning is simultaneous, each individual task has 300 other examples from the 100 of each of the three other tasks to learn from. And normally the cases that there are like a lot of tasks going on. So like if there's 100 tasks and each of them has 100 examples, there's a lot of data to draw from. It also makes sense when you can train a big enough neural network to do well on all the tasks. So normally the alternative would be to train a neural network for each of the four tasks separately. Um, so you could have trained a neural network for each one of the four tasks and use them. But since a lot of the features are the same, you can just use one neural network to do the work for all the four tasks. And it saves time and gives better performance. Uh, Multitask learning doesn't make sense sometimes, and that's when it hurts performance. So if your data set isn't big enough, uh, like if if a big enough neural network can be trained that the multitask learning can use it, it should not hurt performance. But if it can't be trained that way because of lack of data or something, it could hurt performance and it won't be very correct all the time. I did a little research on MTL methods for deep learning. There are two of them: hard parameter sharing and soft parameter sharing. Hard parameter sharing is most commonly used. Um, it's generally applied by sharing the hidden layers between the tasks and keeping the specified, like several task specific output layers. Hard parameter sharing reduces the risk of overfitting. So the risk for overfitting of the shared parameters is an order n is the number of tasks, is an order n smaller than the overfitting task specific parameters. So intuitively, this means like if you have a lot of tasks and you're learning all of them simultaneously, uh, there's more representation that, like, your model has to capture representation that includes a lot more tasks. And so the risk of overfitting is normally larger, but using this method, it reduces. So, like, individual tasks have task specific layers uh, in the output, but initially the layers are shared. In soft parameter sharing, each task has its own model with its own parameters. Uh, but then the distance between the parameters of the model is regularized to encourage the parameters to be similar. So the constraints for use for soft parameter sharing in these networks have been inspired by regularization techniques for MTL. Um, that's it. Any questions? Okay, thank you.
Okay, so we can move on to the next person. Nali?
I can start.
Ariane, just a quick comment. I was not familiar with this topic, but your presentation was very motivating. It intrigued me to look at the literature about that topic. Thank you.
Thank you, thank you.
So today I'm going to talk about neural Turing machines, and I found them very interesting, and I hope you will feel the same about them. So what are neural Turing machines? They belong to the large family of RNNs, and they are neural network architectures that use external memory. These models are able to infer algorithmic tasks like copying, sorting, associative recall, and according to the inventors of this architecture, via NTMs, they extend the capabilities of neural networks by coupling them to external memory resources, which they can interact with by intentional processes. And these models are relatively new compared to LSTMs and RNNs. They were created in 2014. So now I will talk about the motivation for creating neural Turing machines. Even though computer programs heavily rely on logical flow control, elementary operations, and external memory, the modern machine learning almost never uses two of these fundamental mechanisms, logical flow control and external memory. So the authors wanted to use this into machine learning. Now I will talk about the architecture of this interesting model. So NTMs have two basic components, namely controller, as you see here, and memory bank. They use external input and external output vectors in order to interact with the outside environment. This is similar to what we have in a typical neural network architectures. But additionally, unlike other neural network architectures, it also interacts with a memory bank using read and write operations. NTMs can be used with gradient descent, and this process will be quite straightforward as each component is differentiable. So, why is every component in NTMs differentiable? As the authors claim, we achieve this by defining blurry read and write operations that interact to a greater or lesser degree with all elements in memory, rather than addressing a single element as in a normal Turing machine or digital computer. So how the degree of blurriness is determined? There is an attentional focus used in order to limit input-output interactions with relatively small parts of the memory and neglect the other ones. Now I will move to the reading part. So this is also called the read head. And suppose that we have empty contents from any matrix and witty weightings over the n locations which were emitted by Red Hat at time t. So all the weightings are normalized and we will have these properties. And the RT that is returned by red is defined using the following formula. Now I will talk about the writing part. Each write is decomposed into two parts, erase and add. I think that might be like similar to what we have in LSTM, like a forget gate. And actually, authors mentioned in their paper that they used some parts of LSTM's architecture in their model. So we have erase vector et. Its m elements lie in range 0 and 1. And here again, we have these ratings that are produced by memory by right head and memory vectors m t minus I are mt minus 1, I are changed as it is written in the given formula. So I think this formula is pretty self-explanatory because as it is clear from here, both weight and arrays, if they are equal to 0, if they are equal to 1, then we reset them to 0. And in other cases, we don't change the memory. I apologize. I think I should have here mt minus 1i. I forgot that. I'll change it later. After arrays, we also have add vector at that is added to our memory. And we have this formula. Now I will move to the controller network, and this is the most important part of the NTMs because we need to choose the architecture for the controller network. So we can use feed-forward or recurrent network, and if one compares the controller to the central processing unit in a digital computer, albeit with adaptive rather than predefined instructions, and the memory matrix to RAM, then the hidden activations of the recurrent controller are akin to the registers in the processor. It is interesting that if we choose feed-forward network as a controller, we can mimic recurrent neural networks by reading and writing at the same locations at every time step. Now I will move to the addressing mechanisms. So these addressing mechanisms are divided between content-based and location-based, and they are responsible for producing weights by read and write hats. So firstly, I'll talk about content-based one. Heavy focus on location based on the similarity between the values that were emitted by the controller. Here, both read and write hat firstly focuses on creates focuses on a length m key vector kt, and we compare them to mti vectors in our memory bank, and this method produces normalized weights, and the similarity can be measured using this cosine similarity metric, which is quite famous. But as it was described in the paper, content-based addressing mechanisms are not always the good choice, because we might have cases like, suppose that we have this x and y, and we have a function which produces x multiplied by y. In that case, we would need to get these values directly from the addresses, and content-based addressing mechanisms would be a bad choice. So as I already described, content-based methods sometimes is not well suited for the problem, and in this case, location-based addressing is used. Location-based addressing uses rotational shifting and weighting. Before rotational shifting will be performed, both read and write hats produce color interpolation gate GT between 0 and 1. This value acts like a blend between weight produced in the previous time step by read and write hat and the weights generated by the content-based system, and as the result, we have these gated weights returned. And depending on the value of the G, we might completely ignore weights produced by content-based system or by hat in the previous time step. More precisely, if G is equal to 0, we ignore content-based system, and if it is equal to 1, we ignore the hat. And after we will perform this procedure, shift weighting is applied. The simplest way would be to use softmax for defining shift weighting. Rotation that is applied to our gated weights is written using this formula. And in case the weights are not sharp, this convolution procedure can lead to leakage or dispersion. In order to solve this problem, each hat produces additional scalar gamma t, which are more than or equal to 1, and this makes sure to sharpen those weights, and this is the formula for that. So Now I'll talk about the advantages of using both content and location-based addressing in the NTM architecture. We can choose weighting by content-based system without any modification. As I already described, depending on G, we can leave this content-based system as it is. We can choose weighting by content-based system and apply shifting, and weighting from previous time step can be rotated without any input from the content-based addressing system. Now I will move to the part which describes the advantages of neural Turing machines. So they have the ability to learn algorithms, they have ability to generalize, and they have a good performance even if we have huge data. Before I will talk about disadvantages, I would want to show you how NTMs performed on several different tasks. Firstly, I will talk about this copy task. So the copy task tests whether NTM can store and recall a long sequence of arbitrary information. The network is presented with an input sequence of random binary vectors followed by a delimiter flag. Storage and access of information over long time periods has always been problematic for RNNs and other dynamic architectures. So the authors are particularly interested to see if an NTM is able to bridge longer time delays than LSTMs. And here is the picture which shows the results. And as you can see, NTMs with LSTM controller outperform NTMs with feed-forward controller and LSTMs. So they're quite good at this task. So also, repeat copy is similar to the copy, but additionally here we also want to get an output at a specified number of times. And the authors wanted to test if NTMs would be able to learn trivial nested functions. And here you can see the results, and again, NTMs with LSTM controllers are the best. Also, authors use the NTMs for associative recalling. As they have written in their paper, we test the NTM's capability for training an instance of this more interesting class by constructing a list of items so that querying with one of the items demands that the network returns the subsequent item. More specifically, we define an item as a sequence of binary vectors that is bounded on the left and right by delimiter symbols. After several items have been propagated to the network, we query by showing a random item, and we ask the network to produce the next item. In our experiments, each item consisted of 3 6-bit binary vectors. And again, NTMs with LSTM controllers and NTMs with feedforward controller are better than LSTMs, as you can see here. Also, authors tested their NTMs with n-grams. The authors wanted to test how NTMs would perform as rewritable tables like n-grams. In this case, all possible 6-gram distribution over binary sequences were used. The network firstly observes data 1 bit at a time, and then it is used to predict next bit. So as you can see here, we don't have like drastic better results in NTMs with feed-forward controller and NTMs with LSTM controller, unlike these previous tasks. But still, they outperform LSTMs. And lastly, I will talk about the sorting problem, priority sorting, more specifically. So the authors tested how NTMs would perform when it comes to simple sorting algorithm, and the priority was chosen from range -1 to 1, and input contained binary vectors with their priorities, and target contained sorted input based on their priorities. And here again, NTMs were a better choice than LSTMs. So what are the disadvantages of neural Turing machines? This is their time complexity. They are very difficult to be implemented. SOA does not benefit much from GPU, and they are architecture dependent, as you could see from, so we're choosing architecture in our controller network, so they depend on the architecture, and we might have a different results depending on that. And additionally, I also found some articles where it was described that it was neural Turing machines are also difficult to train. And I have an additional note. I was interested how NTMs and LSTMs differed and which one was better, and I found the answer in the Quora, and I have written it here like summary of that answer. In terms of training time, NTM is not better than LSTM. Furthermore, there are lots of things going inside NTM which requires more iterations than we would need for LSTM. And I already explained for you that there actually goes a lot of stuff in NTMs. But in terms of performance, NTM is more likely to beat the LSTM. Theoretically, NTMs can have an infinite memory across time steps. Thus, they are good when we have large data. However, if we have smaller data, LSTMs can be a better choice. Therefore, depending on the task and the amount of input, NTMs can be better than LSTM. And also, additionally, before I would finish, I found that NTMs can recognize formal languages. I found some article, and I will put it lately here. And NTMs can be good at natural language processing tasks. So that was all that I wanted to share with you.
Thanks, Nali. Is there any questions or comments?
Yeah, a quick one. So this was a very interesting explanation. Thank you. But in terms of the performance, when the paper is saying it outperforms LSTM, I feel like, so based on my prior experience, I feel like that heavily depends not on just the time and the data set you're using, but also on the similarity measurements you're using. Like that cosine similarity doesn't necessarily work well everywhere. So it heavily depends on the structure of your data, your data points in general, the features, a lot of different things. And there are multiple similarity measurements to use there to match. But I feel like in general, I personally didn't have a good experience with it. Maybe it was because of my specific use case or the features of the data or the similarity measurements that I tried. But I feel like we cannot necessarily say it outperforms LSTM in all cases if we give it like infinite time. You see my point?
Yeah, I actually have no experience in NTMs. I just wanted to find out how they differed from LSTMs, and I considered Quora as a credible source for that. I will edit it.
Yeah, but that was very helpful. Thank you.
Yeah, Nali, could you please share the screen again? I have a small question.
Yes, of course.
Yes, I saw that you have a node like the NTM versus LSTM, and also
Yes.
And in the picture you shared, there is NTM with LSTM controller. Does it mean that these two can be combined, or?
Yes. Wait a minute. I will move to that part. I have this controller network. In controller networks, we can choose any architecture that we want, like feed-forward or recurrent networks, and LSTMs can be a choice also. So here we have LSTM controller. So we specifically chose that architecture. So do you understand that?
Got it. Yeah. Okay, I see.
Thank you for your question.
Thanks. Is there any questions? Okay, so maybe the next person, Renbeck.
Hello? Hello?
Yeah.
Can you hear me? Yeah, let me share my screen now. Can you see my screen? Can you hear me?
Yeah.
And can you see my screen? Can you hear me clearly? Because sometimes like I can speak very quiet.
Yeah, I can hear it clearly.
So speaking out loudly, I think I don't have any issues hearing you now.
Okay, thank you. So today I wanted to share like my progress on the model. So previously we talked there were notes on sequence to sequence models. Then I later talked about adding an attention mechanism to sequence model. And now I wanted to go a bit further into that and introduce like a new model which doesn't even use RNNs and like whole totally based on the attention mechanism. So once let me first introduce some like references regarding the model is called transformer. So yeah, so those articles are this article called Illustrated Transformer by Jay Alamar. It's a very good article on that. And over here is a paper called Attention is All You Need. The paper that introduced transformer model. Over here is a very good video on explaining also the transformer model. And over here is a tensor intro collab notebook about how to implement the transformer model and how to use it. It's a library based on the TensorFlow. So let's go over how kind of like introduction to the transformer model. So the concept of attention helped dramatically to improve the sequence model, and there was a lot of improvement and development on that concept in those times. And there was those times when two main papers on attention got released. One of them is a paper called "Attention is All We Need." The paper introduced a model called transformer that uses only attention mechanism to work with sequential data, no RNNs. The model they created is subject to parallelization and works very well with GPU. Yeah, because one of the main problems with RNNs before is that we have to first calculate the first time steps and second time step and later, and this we couldn't really utilize the GPU power with RNN models. Yeah, so you can see how it will be easily to parallelize the transform model because it doesn't use any RNNs. As before, it's considered example of machine translation. Yeah, and also as before, model consists of just two parts: encoder and decoders. Let's go over each in more detail. So let's see transformer encoding. So we will consider the transformer model built in the paper. There can be a lot of variations, a lot of hyperparameters, and can be subject to change. So yeah, in the papers they used kind of 6 equal parts, they called encoder in the encoding section, and 6 decoder parts. So they all like identical, but they don't share weight, so it's like layers. Yeah, let's dig into encoder layer and see what is inside. So here on the image, you can see what each transformer encoding part itself consists, and it consists of the 3 parts. So-called cell attention layer they introduced in the paper, just like adding a normalizing layer and just usual feed-forward layer. With 2 of those, we're already familiar, just feed-forward and just normalizing. Let's go into deeper into self-attention layer. And in order to understand self-attention layer better, I'll divide self-layer understanding into several parts where I'll be modified. I'll just take a sequence model, encoding part and decoding, and then like modify a bit to get to like concept of self-attention. So the first step in understanding the self-attention layer would be to basically get rid of the RNNs. Yeah, just yeah. So over the first step, for each word embedding, so because we're considering the machine translation, we just take this current, as you can see on the picture, this current time step, this current embedding. We take some, let's say, uh, we take some uh, scoring attention function and score uh, each other vector in a input. So here we can we get all the scores, and also we have to divide by the square root of dimension of those vectors. And this is this is a trick that should help gradients to be more stable. We didn't use it before, but they use it in this paper. Then we, as usually before, we take a softmax of those and sum it up. Then we also sum it up to the current time and time embedding, and over here, and that would be our output. Yeah, so this is like how we would use attention mechanism and kind of get rid of the RNNs. Now let's see what's kind of wrong with it, because next step we would introduce keys and queries. So now if we look at the previous modification, in this case the word similar to the current one. Let's say if we use like just a dot, usually like in this case people would use just a dot attention function, and it just would be, so the scores for the similar words would have bigger scores uh, to the current one. But what we actually want to have scores of relevant words to be bigger. So we need to add some kind of like learning aspect to it. So yeah, we're adding the concept of keys and queries. So keys and queries is kind of we can think about just like a multi-layer perceptron without like any activation function, just or just usual magic multiplication. Magic multiplication weights that we're gonna learn eventually, like with backpropagation and stuff. So over here you can see that when we with the current time step we're gonna pass through the query MLP, and all others we're gonna put on a key MLP, like just one matched multiplication. Then later we just gonna use the previous process of taking each other vector, scoring the attention function with the current time step vector. We're gonna also divide by the square root of dimension of the keys, because also the keys and our queries should have the same output dimension. We're gonna take softmax and sum it up with the current time step embedding, and we get this. We'll get the output of that. Output, kind of current encoding output, like in an encoding decoder with attention. Now let's get add values. So the previous algorithm with keys and queries can work well, but the paper also introduced another modification. And in this case, we will calculate the scores based on keys and queries like before and take softmax of those. But instead of adding the input vectors multiplied by the scores, we'll add another MLP/matrix called values. So we'll pass those embedding through the values matrix, and we're gonna output would be weighted sum of those outputs. So the weight would be the scores from the softmax, which is based on keys and queries, and the actual vector would be output of the value matrix. Now we kind of get kind of single attention layer kind of concept, but they also introduced another modification, which is called multi-headed attention. In this modification, we just used several of previous algorithms. Like we initialize several keys, queries,
I cannot hear you. Can other people hear?
Yeah, I can neither. Hi, Rembek, dear. Mm. Hi, Renbeck. Can you hear me?
Maybe he should comment if he can hear us, because I can't hear him.
Yeah. Oh, he has left the meeting. I think he will join again very soon.
And you, a quick question. So are you going to explain Jing's project as well?
You mean Jing's project?
Yeah.
Yes. I think after the presentation, I will say something about that. Yeah, I don't know.
Great. And Jiayun,
I don't know the details, but I will.
Jiayun, you have been.
Yeah. She told me that she is seeking for one to two more people to join the team.
Yeah, so Jiayun was working with Jing on that project, which is basically, so we'll discuss that project a little bit later. It is something related to One Academy, but I feel like what Reinbeck was explaining can be very helpful in that project. So I feel like if you want to introduce that project, maybe it's a good idea to introduce it after Reinbeck finishes his presentation. And then Jing is not here, but you can, if you have any questions about that project, you can ask Jiayun and I, and we'll be happy to explain that.
Sure. So maybe now we can just wait for Rainback.
Probably he lost his internet connection. So do we have any more presentations for today?
Seems there are not.
Can you repeat that? I couldn't hear you.
Oh, pardon?
I couldn't hear you. Can you repeat that? So do we have any other presentations for
No,
today?
we don't have other presenters. No.
Okay, got it. So you,
Oh,
I
I'm
don't
sorry.
think we should.
Where did I
Oh, he's
stop? I
back.
kind of like I told the whole like I went through the whole presentation. I didn't notice I was out.
oh my God. Yeah.
At what
Could you
point
please
I did
share the screen again? And I think we can't hear you from the multi-head attention part.
I see. So it's like probably like the beginning. So uh, is it this note where I got disconnected?
Uh, yeah.
Was it
You
this
can
note
start.
or?
I think you can start from here. Yeah.
Okay. Yeah. So previously we like so far we got introduced to values and keys and queries, and this makes like the basic self-attention concept. So it concludes the basic self-attention complex, the self-attention layer. And in the papers also introduced kind of modification of that also, because they're just gonna use several of those in parallel. So now we initialize several matrices of keys, queries, and values. We pass all the words through all of the different self-attention layers, and we're gonna get several. So in the papers they used 8. So we're gonna get several outputs of the self-attention layer. We're gonna just concatenate those outputs. We're gonna pass it through the another matrix. So the output matrix would match this each of the self-attention outputs, and that would be our output of the multi-head attention. So it's just multi-head attention, just using several self-attention and just kind of concatenating and uniting all the outputs from all of them. And one of the main advantages of that is that we can focus on different positions for each of the input vectors and understand the connections in between the words in different contexts. Like we can look into different dimensions of one context of each word. Yeah, so as you may notice before, we didn't really use any information about the order of the words, because we just take each word and compare it to all other words, and that's how we get the encoding vector. But but now we just need the order is very important, because just if you change the order, it just may change the meaning. So we need to add somehow the time sense to the inputs. So, but without using RNNs, because RNNs would ruin the parallelization. So instead of using RNNs to account for the order, we're gonna add a variable, the change variable, which depends on the timestamp to each of the embedding inputs. Yeah, and I wasn't able to get into how this calculated exactly. So here's an example of how this, like the variable is calculated for 20 words with the embedding size of 512 columns. So over here you can see yellow is 1, and more blue it gets is 0, more more blue it gets is like -1, and in the middle is 0. So yeah, I'll read, like, this is subject to more research. You can take into account more of that. So that concludes like the encoder part. So now we know all the parts of encoder, the self-attention part and multi-head attention. Let's look at the decoder part.
Oh my God. I don't know. I will drop you a message and hope you can see it. Okay, I think while waiting for him, maybe we can have a discussion about how the research would be like how we will review the papers. Uh, like if several people is working or going through the same paper at the same time, I think they may if they both want to add a node for the same concept on one academy, like maybe simultaneously, they may don't know that each other is working on that. So how can we solve that problem?
So I think that is already solved on One Academy. Like there are, so since the beginning of summer, there have been many researchers doing COVID-19 research who were working on the same or similar papers. And it's totally fine. Like when you want to propose anything on One Academy, you first find the most relevant cluster of nodes, and there you find direct prerequisite nodes, like the which parent node you want to choose to propose that new node under. And so when you look at that parent node, um, so first of all, if what you want to propose already exists, someone else has proposed it, you don't need to propose it again. I mean, you shouldn't duplicate anything. And so if you can just look at that node, if you find it very helpful, you can just upload it. If you feel like you can uh, improve it, like add content to it or update the content or anything, you can propose an improvement on the node. And so basically, I don't think there is any problem with working on the same paper. Like you're reading a specific paragraph of a paper, like its analysis, its method, whatever, and you want to add it to One Academy. Again, so you go through all the map, the different clusters, you find like the most relevant cluster, you find the direct prerequisite node. If what you want to add already exists, you don't add it, you just improve it or vote on it. If it doesn't exist, you propose it and add it to the map. And this way, there is no problem with having multiple people working on the same paper.
Okay. So now we have Rimbat back. So
I'm so sorry for that. I'm
Rimbat,
sorry.
is there a way that I can let you know that you are out of the meeting? Yeah.
Oh, I see
Like
your emails now. Yeah.
okay. So if you leave again, I will still send you another email.
Okay, I'm so sorry. What
Never mind.
At what point did I exit it again?
At the decoder part.
So yeah, it's not that. So let's go over decoder again. I'm sorry. So over here, you can
Sorry,
see the.
we can't see your screen.
Oh wait. Oh, so sorry for that. I don't know why. It's just like the internet connection is stable, but I don't know. Just exited somehow. I have no idea. Can you see my screen now?
Nope.
No. For some reason, I cannot like press on the present now button.
Or I can share my screen.
Okay. Yeah, there's only 2 nodes left.
Okay. It may take some time.
I'm so sorry for that.
Okay, so the name of the node is
Decoder. Name of the model transformer decoder.
okay.
So can you just pause right here? Don't close the search sidebar. So this is for everybody. When you're adding a node title, please pay attention to this, that later on, people are going to search your node. and like only decoder, like the title only like one or two words is not that helpful. Like when I search something and I see the node decoder, it doesn't tell me exactly what this node is about. You see my point? Like add a
Yeah, I see,
lot
but
more information, like in sequence learning, in like RNN, and it's like add something that uh, distinguishes that node from like other similar nodes.
yeah, I see, but yeah, I put the like transformer decoder, so it's like saying the decoder of the transformer.
Yeah. So if you can add a little bit more information to your node titles, that would be great. Thank you.
Hmm.
Would you like to start?
Yeah, I'm waiting until like we get to the. Yeah, I'm just waiting until we get we can see the one academy.
Oh, yes. Actually, we can see it already. Can you see? Can you see it?
I can't I cannot see it.
I, uh, I think I have put the transformer decoder node on my screen now.
Can anybody else see it? Because I just seeing like, yeah, I'm not seeing anything.
So if you have internet connection difficulties today, Yua, do you think it's a good idea if Rainbeck continues his presentation next week?
Sure, I'm okay with that.
Yeah, I think that is a better option so that we can continue with discussing the research projects and
Sure.
you can continue presenting next week. Rainbeck, does it work for you?
Okay, then I'll just add more in like more context and more information to it.
Thank you.
Also add
Sure,
the
and
note on my guns.
yeah, thank you, Renback.
I'm sorry for internet connection. I don't know what is happening.
Yeah, Iman, actually the question previously I asked is that if two persons are making the same proposal at the same time.
I have never seen what happens if they do at the exact same time. I don't
Okay.
think that is like that is an extreme case. I don't think that will happen a lot, but I don't know what happens if they do that.
Sure.
I don't think it is practically possible because like one of the proposals would be received by the cloud service earlier than the other one in any way, right?
Mm-hmm.
Like exact same time is only possible in theory, not in practice.
Sure, got it. And another question is that, like, for a paper, maybe someone is working on the introduction while the experiment node is made one another person. So who will make the presentations?
So the way it works in most of our meetings and like research groups and my classes is that we go through nodes in the network graph structure, like in the knowledge graph structure, right? Not based on person to person. We just continue in the knowledge graph structure. And when we reach out to any node that is designed by any specific person, that person will present that node. You see my point? Like we don't go through list of presenters. We go through the network of nodes and links, and whoever wants to present a specific node, they just turn on their microphone and they talk about it.
Okay, got it. Okay, so next I will say something about Jing and Javin's project. So you can see that Jing has added one more paper idea the sixth one in our detailed research plan.
I'm sorry, for some reason I cannot see your screen.
Yeah,
Can
you
everybody
can.
else see?
Can everybody else see?
I can.
Okay, Renback, you can go to detailed research plan. The document.
Let me exit and enter again. Maybe in this case, I'll
Yeah,
exit.
you don't need to, Ramback, you don't need to look at you as a screen. You can just open the detailed research document on
Okay.
Microsoft Teams.
Okay.
But feel free to like just close this session and open this session again on Microsoft on Google Meets, because I feel like that may help.
I see. Okay. Yeah, I was just like, for now, I'll just open the file.
Okay, yeah, there is a new paper idea in the file. That is the One Academy bot, and I think Iman, Jing, and Jiayun are working on this now, and they are seeking for one to two more people to join their team and to working on this project. And Iman, would you like to introduce something about that?
Sure. And Jian, do you hear me? Jian? Jian, do you hear me? So probably she doesn't hear me. I was just wondering. Okay, so I continue explaining the project. So everybody in this team has used One Academy at some point, and some people have used it more, some people less, but you know the idea of prerequisite links between concepts on One Academy. That is the basic idea behind One Academy. So the question is, there are hundreds of COVID-19 publications every day coming out in different journals and conferences and conference proceedings. So far, starting early in the summer, after the COVID-19 outbreak, we used One Academy. I mean, a fairly large group of students and researchers in different schools used One Academy for doing literature review on COVID-19 research. Although they have been successful so far with just summarizing their papers of interest, sharing what they understand, their interpretations and summaries of each paper with the rest of the community, and they found it helpful. However, the problem is we have only a certain number of people in the community, and they cannot cope with all the publications that are coming out every day. So the problem is, how can we develop a model that identifies the best prerequisite node on the map for any newly published paper based on its abstract? So the input data is kind of a transformation of the One Academy knowledge structure, like all the nodes and their links between nodes, right? And the abstract of a new paper. So the output of the model would be the ID of a specific node on One Academy, which is the most direct prerequisite node for this specific paper abstract, right? So assuming that for this specific paper, we want to only propose one single node, where should we propose it on the map? This has been the topic of interest in multiple deep learning and in general machine learning conferences in the past few years. I mean, in recent years, that they were trying to identify prerequisite relationship between concepts in text, in networks of, in research networks, in many different domains. So we have a specific context here. We have a fairly large training set of all the nodes, and we have more than 10,000 nodes and links between nodes that are already identified and added to one academy by students and researchers, experts, and so on. And so we can train a model based on that currently available data to be able to predict the best prerequisite node for a newly published paper. That is the basic idea. It is not an easy project. It is not trivial. It is very interesting for the community because you can find a lot of recent papers about the topic, and people are interested in like there is a trend in the literature, not just in machine learning literature, but in computer science, in HCI, in all of these communities, there is a new trend in visualizing knowledge, like knowledge graphs, identifying links between concepts, between pieces of information. And it makes sense because one of the biggest, 50 years ago, we were dealing with difficulty with accessing knowledge. Now we are now that need is obviated. Like we are not dealing with that difficulty anymore. We have access to abundance of knowledge. Now we have another problem, which is cognitive overload. Like we have so much accessible knowledge that we don't know how to organize it. There are a lot of repetitions, contradictions. It's very time consuming to find anything to learn from, like to find organized the stuff that you're looking for to learn from, and like understand how they're related to each other. So in order to facilitate knowledge organization, like management, and facilitate learning and understanding through this abundance of knowledge, there are multiple trends of work. One Academy is one of them, to visualize knowledge in a collaborative manner, right? And so if we can find an efficient mechanism to do this, I feel like the result would be a good paper. But it's not going to be easy. We still don't have, so over the past couple of months, we didn't do that much work on this. I feel like the last time, Jiayun, do you hear me? Jiayun? Still, she cannot hear me.
Yeah, I hear you. I just I mute myself.
Okay, so do you remember when did we work on this the last time before we joined this larger group?
Yeah, I think we're still like reviewing literatures because that we have some hard time understanding some part of the literature. So you said it'll be helpful if you can learn this deep learning course.
Yeah. So now that we are returning to our smaller groups to work on research projects, so this is one possibility that Jing and Jian have been working on, and they're going to continue working on, as far as I know. Is that right, Jian, or you prefer to work on something else?
Yeah, I think I'm still gonna work on this topic.
Great. So if anyone else is interested, Jing has already explained a summary of the project on this document, and you can see it on Yua's screen. And if you're interested, just let us know. We're looking for, Jing and Jiayun are looking for 1 or 2 more people to join their team. Any questions about this project? Questions?
No, everything was quite understandable.
Yes. Yeah. Like just to summary, there are two possibilities to move on. One is the one Academy bot, Iman has just introduced, and another one I think would be our third paper idea, like improve human learning with deep learning models. And I will be continue with the third one, and I think very soon I will send invitation messages to anyone I'd like to invite to join this research group. So yeah, this is for this research group. And for the One Academy bot, if you are interested, please you can directly contact Jean to talk with her about that. Yeah. So is there any questions about this?
Do you have other topics to discuss today? If there is nothing else, I have something to explain about the third project.
Sure. I don't have other things. You can. Do you want to presenting?
Yeah, can you go back to that page on your screen? Yeah, right here. Okay, so 29 minutes ago, I shared that data set with you. This is, I don't think you can open it here.
Oh, yeah.
This is 380 megabytes of data.
Oh my God.
Yeah. So, and this is a small data set for what we are going to do. We have a huge data set that I didn't share with you because it's not practical to share unless we really need it. I have to find a way to share it. This data set is only for 4 semesters in one Python programming class. This is the log data of usage of the practice tool by 200 students in each semester. So it is around more than 1,000 students. The reason it is huge is because it's not huge, it's large amount. It is because for each student, for each of these 1,000 students, we have many log data points. Like this student at this specific time on this day answered this specific question from this chapter and this subchapter, correct or wrong. You see my point?
Yeah.
So it is basically a log file, but it is not a raw log file. I actually spent all this morning trying to merge multiple data sets to create this data set, and I anonymized it. And I tried my best to make this data set as understandable as possible and as easy to use in a deep learning model as possible for you, so that you can start from there. So the vision of this project, excuse me, I told you before. The vision of this project is to study how we can use deep learning models to improve human learning. There are several studies going on about this. This is an active topic in the literature, in both cognitive psychology literature, neuroscience, and machine learning. There are a lot of papers using different machine learning methods. I'm familiar with multiple deep learning methods, but most of those studies are on language learning. we are one of the very first ones who is looking at how to improve learning of a college level course, specifically in programming. I'm not familiar with any other study. Now, if we're successful in the next few months, first of all, working on this means we're going to publish multiple papers. If we're successful enough in the next few months, we can publish a good paper, like we can at least submit a good paper to KDD conference or ICML conference, which are very prestigious conferences in deep learning and machine learning. However, usually when I start a new project, I have a specific strategy that I want to share with you. You can decide whether you want to take that or not. Everything is based on your decision. So that strategy is when I start working on something new, I usually try to start with a very simple idea to try to publish it in a fairly moderate conference, like submit it to a moderate conference. By moderate, I mean prestigious enough, but not one of the top tier conferences, so that I can get involved in the community. I can get in touch with what other people are doing. I can get feedback from them. I can have, so that is basically, and also one of the reasons is I feel like having short deadlines is extremely helpful, at least for me. Like defining multiple deadlines throughout like a project helps to focus on the project, helps to like motivates at least me to keep going on the project. So I feel like it's a good idea to start with finding a very close conference deadline to only focus on how can we train a model, a deep learning model, to predict when each student is going to forget each of these questions based on this data set that I've shared with you. And I believe it is interesting enough that we can publish it very soon. Now, the question is, among those who are interested in working on this project, how much time can you dedicate to it?
I can dedicate as many time as it would be required or needed. Like maybe 15, 20 hours per week.
Okay, so everybody else, how much time can you dedicate to this project over the next few weeks? And we are starting with a very simple idea, nothing complicated. We have a data set to use. It is large enough to be usable, and it is not too large that we cannot manage it. It's only data for 4 semesters in a fairly large course. So I feel like the size of the data set is manageable on your personal computers. You don't need any server or anything like that for analyzing, like not analyzing, for training a model based on this data set. It is manageable. If you have any difficulties, let me know. I will be able to help you with that. Now, so the basic idea is we want to train a very simple model based on this data set to predict if we ask this specific question, like question A, from the student B, at time C, would the answer be correct or wrong? Like, would this student be able to answer it correctly, or the answer would be wrong? That is the basic idea. So we need a sequence model like LSTM or something like that, because we are dealing with the matter of time and the previous history matters for this specific student. And I feel like it's not difficult to finish this project very soon and submit it to a conference. Now, my question is, who is interested in working on this project first, and how much time can you dedicate to it? So, Niley said 15 to 20 hours per week. She's interested. You, are you also interested?
Yes, I'm interested. Do you mean
So
in the next few weeks?
What is that?
Do you mean in the next few weeks?
Yeah.
My
So to be very precise, how much time would you like to spend on this project this week?
I would say about 8 hours.
Okay, 8 hours this week. Others? Anyone else interested in this project?
Or do you need more time to make decisions? You can also.
I want to get feedback from everybody, and then we can decide on that. Anyone else interested in this project? So I'm assuming that only you and Ninely and I are going to work on this project. Is that right? So Nikhil, Robang, and Jiayon, you're not interested in working in this project, right?
Wait, sorry. I am interested. It is that I feel like I might need a little time to read a few of the helpful papers to kind of figure out get a better understanding of it. But I can probably do another also 8 to 10 hours.
I couldn't hear you. How many hours per week?
8 to 10, I think.
Okay.
Yeah, I'm also interested. I'm maybe for like a couple few weeks. I think I can have 8 to 10 hour 8 hours. Yeah, right.
Okay.
Let me check. Robin, are you here now? Okay. Actually, Robin has told me that she is now in China, and now it is 3 a.m. in her time zone. So yeah, so maybe I will check with Robin and Renback later privately, and I will tell you the their answers.
And so do you know if Renback is also, I think in the document, Renback is also saying he's interested.
Yeah, he also said that he is interested.
Okay, so who else is going to, how about Aryan?
Aryan, when did they leave the meeting? I'm not sure.
Yeah, I'm not sure either.
Yeah.
So can you do something? Can you send a message, like an announcement in the channel to everybody who is interested in this, in working on this project, and ask them how much time they can dedicate to it this week? And there is a reason I'm asking this. Because I believe we can write a very short paper about such a model very fast to get some like energy to start working on the project. That is usually
yes,
what
I am.
every project. What is that?
Go ahead. Yeah. Go ahead. Yeah.
Yeah, I am not sure either. So you, can you do something? Can you send a message, like an announcement in the channel to everybody who is interested in this, in working on this project, and ask them how much time they can dedicate to it this week? And there is a reason I'm asking this. What is that?
I'm wondering, which conference do you mean? I mean.
It doesn't matter. There are many conferences we can submit this to. We are not looking for, so for the very first attempt, we are not looking for anything ambitious.
Okay.
Just a very simple model, probably an LSTM model, that can give us a fairly good prediction of when each student, or not when, whether student A can answer question, can correctly answer question B at time C. That is the simple question, right?
Sure, yeah.
So, so the other question is, I've already shared a couple of papers with you on this document. Is there anyone who has gone through either of these papers?
I read first paper, Accelerating Human Learning with Deep Reinforcement Learning, and I started yesterday reading second paper, but I only read like few pages of it.
So have you already summarized the first paper, the 2017 paper on Khan Academy?
Yes. I have several notes for that, but I had some difficulties with several formulas in that paper, and I will again review those notes that I wrote.
What do you mean by having difficulty with formulas? Like you had difficulty understanding the formulas or writing on one pad?
I read that paper approximately a week ago, and I had like no background in deep reinforcement learning, so it was very new for me. And I started in this week reading the paper which you had provided in One Academy, and now I have a better understanding of that.
Got it. Okay. So
yeah. I haven't started with the papers, and I think we can make sure what paper we are going to discuss in the next week, so everyone can work on a paper. Read that paper, yeah.
sure.
So
I think I can present first paper in the next meeting, but I'm not sure that I would finish the second one because it was approximately 96 pages, or I don't remember exactly.
oh. How do you think?
Maybe I can manage. Maybe I would let you know about it.
Yeah. What I mean is that I will post an announcement for everyone to actually read the paper before the meeting, so it will be easier for everyone to understand and also discuss about that. So, do you have recommendations of which paper to discuss in the next week? I think the first one, and do we need to add another paper?
So let me clarify something. Can you scroll up a little bit?
Up?
Yeah. Go up, please. So yeah, you see that a personalized retrieval practice tool in the first line of the description, right? So that is a very, very easy to read paper. It has nothing to do with deep learning. That is the basic explanation of this practice tool, that the data set is coming from that practice tool.
Okay, so I think at the very first we should read this paper.
Exactly. So that is like you can read it in like 30 minutes. That is very easy, right? So I expect everybody to first read that paper, understand what's going on, understand what is the practice tool, how it works, how it currently works, and then before going through the rest of the papers, I expect everybody to go through the data set.
Sure.
Get a good feeling of the data set. And I think it will be a good idea if can you create a file for description of the data set so that we can start collaboratively filling out that file, that text file in the same folder to just explain what we understand from this data set.
Create a
Yeah, if we can just create a Word file here so that for each of the variables in the data set, we can explain what that variable is or how we can use that variable and so on.
So how would you like to name it?
So variable descriptions, you can call it a space repetition. You can call it a space repetition variable descriptions. The reason I'm calling it a space repetition is because most of these studies in the literature are called space repetition, which is a very, very old algorithm for improving learning. The space repetition, right?
Variable description.
Explanations, right?
Explanation.
And so the first word is spaced with D, right? Yeah. So everybody can just start adding variable names. We can create like a bullet point list of variable names and explanations for each variable and how we want to use it, or any clarifications about any like data points. If we see like a lot of issues with a specific variable, we can discuss how to fix those issues and so on.
Sure.
So are there questions, or I can just walk you very quickly through the data set? Any questions?
I don't have any.
All right, so I'm going to open the data set and walk everybody through the variables very quickly so that we have a high-level understanding of what's going on in the data set. Okay, so the first column is basically just indices, nothing interesting. Second column, term. So we have 4 different terms in the semester, starting winter 2018, then fall 2018, winter 2019, and fall 2019. Again, this data is coming from an introductory to Python programming course with on average 200 students in each semester, right? Now, the second one is their final exam grade. The third one, these are very similar things. Final exam standard deviation, final exam percentage, final exam between 0 and 1. These are the same numbers, like very, very similar, like correlated numbers. You can infer each of them from the other one. So nothing interesting. Next one. Yeah, and this log transformation of final exam. That is for the purpose of that is inverse log transformation of final exam to make the distribution normal. That has a normal distribution. Otherwise, like other columns about final exam, none of them have a normal distribution. Next one. Okay, so this is final course grade. Again, similar to final exam, we have the same types of transformations on final course grades in the next few columns. So it is basically the course grade that was converted to an a letter grade and was transferred to a student's transcript. So what students see in their transcript is a transformation of this course grade, right? Now, I believe these set of columns, final exam and course grade, may not be that helpful in our models. However, if someone finds anything that can help from these columns, they can try using it, but I feel like these are not really helpful. And in terms of practicality, so the ideal case is that the system would be implemented in large courses, and it is not practical to have a student's final exam grade or course grade when predicting what questions to personalize for each specific student to answer at each period of time. So not using these columns, like column C to K, is a reasonable idea. So I don't suggest you to use column C to K in your deep learning model. However, we have this data so that for any reason, if someone wants to reconsider this decision, they can think about it. Okay, next one, practice. Means how many days of the semester this student used the practice tool. Is it possible for someone to just take note of what I'm saying?
I can put it in.
If it is possible for you to take note, I can share my screen and I can continue presenting this using my screen sharing.
Oh, great! I will take it in the sheet in the document we have just.
That would be great. Okay, so let me share my screen. Let me know if you see the Excel sheet on my screen.
Yeah, I can see that.
So you see the data set, right?
Yeah.
Okay. So again, very quickly. So obviously, the first column is the indices. The second column is the semester or term. It has only 4 values: winter 2018, fall 2018, winter 2019, fall 2019. Columns C to K are not useful in this specific use case. They are final exam grades and course grades for each specific student. And so I don't think we need to use these in our deep learning models. Note that each row in this data set represents a single student's interaction with the practice tool, like answering a question on the practice tool by a single student. So that's why you see all of these values are repeated, because these are all for the same student, right? These are characteristics of the same student. Obviously, they should be all repeated. Now we have column L, which is practice. That means the number of days this specific student used the practice tool throughout the semester. Practice score, I don't think we need to use practice score either. This is based on the practice column. So each instructor defines a formula to use on the practice column to convert it to practice score. So we don't need to do this column M either. Now column N is so starting from column N, we have some demographic data about these students. For example, column N is their parents' gross income, like their family gross income. And by the way, the data set is anonymized, so you can use this for the purpose of analysis. So the problem with column M is with column N is that there are a lot of null values, a lot of missing data points, because these are self-reported by students. Column O, it is the very first semester this student enrolled at the University of Michigan. Next column, permanent country for international students it indicates their country of origin, right? So I'm not seeing any international student here. So if you find any international student, that the corresponding value in that column would be like their country of origin. We have high school calculus taken. So this is a dummy variable, 0 or 1. If it is 0, it means they didn't take calculus in high school. If it is 1, they took. High school GPA, it is obvious what that is. High school state. This can be interesting, especially in the state of Michigan, because there are many undergraduate students from the state of Michigan. So it is interesting to see whether this student is in a state student or out of a state student. Like, are they coming from another state or they are from Michigan? Now we have a lot of columns here, starting from column T. So columns T, U, V, W, X, Y, Z, all the way to column AD. These are test scores for ACT and for AP and SAT test scores. Many students don't have these scores, so you see a lot of missing values here, which is very common. Like, there are a lot of students who don't take these tests, which is totally fine, right? Next column, we have whether this student was, is a native English speaker or not. This doesn't mean they are international students or not. Someone may not be an international student, maybe a domestic student, but they're not native English speakers. That is possible. The next column is, again, maximum stat calculus score with a lot of missing values. Next one, maximum TOEFL total score. Again, a lot of missing values because TOEFL is only valid for, it is only practical for international students. Not all international students, some of them. Then we have public math score. This is, as far as I know, this is a test that almost all undergraduate students, when they enter University of Michigan, they need to take this test. And I feel like we don't have a lot of missing data here. I think almost every undergraduate student has taken this test. So, Yua, have you taken this test or not?
No, I haven't. I'm a transfer student. I come here when I'm a junior.
Got it. So anyone else? Do we have any undergrad student from U of M here who has taken this?
I haven't taken it either because I also transferred last year as a sophomore.
Interesting. Okay. Then we have number of dependents in their family, like parents' dependents. Again, this is self-reported. So there may be a lot of missing data here. So if you see a lot of missing data, you don't need to necessarily use this column or like parent or like family gross income unless you feel like it can significantly improve your model. Then we have, this is, I feel like this can be a valuable one, although this is also self-reported and we have a lot of missing data, but I think this can be valuable, which is maximum education level of parents, right? And then we have another one, which is also self-report, whether this student has single parents or not. Like if one of the parents is deceased or they are separated, like they are divorced. We have birth month for this student. We have birth year. Their citizenship status, column AN. U.S. citizenship status. So citizenship status can be any other country, but U.S. citizenship status is specific, so there's a subset of the previous one. Whether this student is considered among minority groups. I feel like this can be a very valuable one. And I believe we don't have any missing data here in this column. I think this can be a valuable one. Then ethnicity is definitely very important. Gender is extremely important, and I don't think we have any missing data here in these columns. Whether they are international students or not, 0 or 1, binary. Academic level, and by the way, you know that you need to use like one-hop encoder or something like that to convert these categorical variables to like binaries or somehow enter them into your deep learning model. Okay, so we have academic level. This is something I generated from other fields, so junior, senior, sophomore, and senior, like one of those levels. We have major counts. This is interesting. So there are few students who are studying multiple majors, not few, like there are a fair number of students who have like double majors, or few students who are doing like 3 different majors. We also have minors. There are students who are doing a major and a minor, or a major and 2 minors. So this is the number of minors, minor count. Then we have academic load. So whether this student is full-time or part-time, whether this student is athlete or not, career level, whether they are undergrad or graduate students. I don't believe we have missing data in these columns. For something like athlete, so if there is nothing listed, it means they're not athletes. So obviously, this is not considered missing, so you need to replace it. We have cumulative GPA. Honors program, this is also a dummy, so whether this student is a member of the honors program or not. So now we have multiple programs. What is the primary program that this student is enrolled in? For many students, we have literature, science, and art, because that is their primary program. This is different from major. Like under each program, you have a major, right? Major was here, right? So this was the number of majors. We will have the exact major later. But again, so this is kind of like department, the primary department. And then program, yeah, exactly the next column would be the major. For example, for some of these, so for many of them, you see literature, art, and science department, like program, and then under that, the major is also literature, arts, and science, general. But there are also many students who are in the literature, art, and science department, but their program is like computer science or something like that, like something else. I don't know. And then we have program 1, major 2. So which means if this student is doing double major, what is their second major? For most students, this is just empty. Yeah, for this student is doing double majors, I think. Yeah. Then we have program 1, minor. If there is for this student it is empty, like it is missing because this student doesn't do any minor in program 1, and minor 2 if there is any. So program 2, if they are enrolled in different departments, like there are students who are doing math and computer science or something like that. So for those students, there will be 2 different programs. And then program 2, major 1, program 2, major 2, program 2, minor 1, minor 2. Now, career would be, I think career is repeated, isn't it? Oh, this was career level. I don't know the difference between career level and career. Oh, this is a combination of program and career level. I don't think that is useful. Oh, residency is useful. So whether they are out of state or in-state students. Then residential college can be also helpful. Term credit GPA. Oh, this is interesting. So it means how many credits does this student take? Is this student taking this semester, like in the semester of the study, that count towards his or her GPA? Because you may take some credits that don't count towards your GPA. So these are the number of credits that count towards your GPA. And then we have term credit, non-GPA, so the number of credits that don't count towards your GPA. And then we have catalog number of the course, so you can just easily miss this column. This is 106 for everybody. You don't need it. The same thing about this one. You don't need these two columns. This is just the indicator of what class it is. You don't need it. You need this one. This is important. I feel like this is a repetition of the second column. Yes, that is a repetition of column B. It's just term. I was merging a lot of different data sets. That's why I missed some of these. Number of students. Okay, so up to here we were talking about the student attributes. Now from here on we are talking about the class attributes. Like this class, this is specific in this specific semester, had 209 students. The average GPA in the class was 3.29. The class was graded, so you don't need this column. Class honors, you don't need this column either. This is like total number of students in the honor program in the class. I don't think it helps at all. Okay, so when was the class started? Like the start date and end date? I don't think it helps either. It may help comparing. Yeah, this may help because we are using a time series. Like in this data set, we're dealing with time series, and we're looking at when each student answered each question. So it is important to take the start date of the class as the baseline and compare like that date with the baseline. I feel like these two are important columns. And then class section code. So which section, like which discussion section this student was enrolled in, because it is a large class, it has multiple discussion sections. Course students know, so I feel like this is the same, yeah, this is the same as this one. Again, repeated. Class type, you don't need it at all. Yeah, I don't think you need this. Course GPA is again repeated. This is the same as this one, as class GPA. I think they're the same. Grade, okay. So this is the student's grade. So this is specific student's grade in this specific course. Obviously, we have only one course in this data set. So this is the student's grade. This student took an A. So these are, again, so we are done with class level attributes. These are from now on, we're talking about the student attributes, but not demographics. The student's educational features. So their grade in the class, A. So I don't think we need to use this because this is at the end of the semester. However, we definitely need to use this one, excluding class GPA. This is extremely important. We shouldn't miss this in our model. This means excluding this specific class, what was the cumulative GPA of this student? Like in the beginning of the semester, for example. I believe at the end of the day, you will find this very helpful. Okay, so you can easily ignore this column. This is like whether this course for this student counts toward their GPA. You can easily ignore this column because we have this column, which is much better. And we have repeated. So what repeated means is whether this student failed the class and is taking the class again. So they're repeating this class. Because this is a required class in the School of Information. So if they want to enter a School of Information, they have to pass this class. This is a requirement. And there are many people who fail and take it again. We have grading type. This is the one that I told you is way more useful than this. You can easily ignore this, but you need to use this one. What this says is whether this student was taking the class for a grade or not. Because there are many students from different departments who are taking this class. Some of them are taking it for pass or fail, not for a grade in their transcript. Then we have their section. Section is like winter 2018, section 4, like rich discussion section. And semester, whether winter or fall, what is this? Semester winter, like there's a dummy for this one. Like for some reason I did this. Like whether the semester was winter or not. If it is 0, it means it is fall semester. Instructor, we have 2 instructors alternating teaching this class. So we have instructor 1 or instructor 2. Whether it is instructor 1, again, a dummy for this one, 0, 1. Practice tool, so you can ignore this. All students had the practice tool. You can also ignore this one, treatment. Okay, so female, this is a dummy for the previous variable that we saw, the gender. So if 1 if female, 0 if male. Non-native English speaker, again, these are basically dummies for the demographic variables, useful demographic variables that we saw before. So nothing new here, but they're very useful. Parents max education, again, these are dummies for. Other than this one, I feel like this is repeated, but oh, this is also a categorical for kind of like a dummy variable. Yeah, this binary, but with a string in it. So this has only 2 levels. These are all dummies for the demographic variables that we saw before. So I'm not going to explain them again. They're obvious. And so this is a 3-level discretization of their prior GPA, whether they are in the low achievers group, mid achievers group, or high achievers. And whether they're taking the class for pass or fail, that is, again, a dummy for the previous variable. I don't explain any of these. These are repeated. These are also, they're not repeated. I mean, they are transformed. You can decide whether you want to use these columns or the previous columns that we saw before. We have, okay, so these are the most important final columns. So these are the final columns, and these are extremely important. We are out of time. Do you have 5 more minutes to learn about these? These are the extremely important columns that we need to definitely use in our model. Any ideas? Do you want me to continue, or you prefer to stop here?
I mean, if it's only like 5 or 10 more minutes, I definitely have time to, especially if these are very important, right?
Everybody else, do you prefer I continue, or?
Yeah, I think we'll continue. And if you have other stuff, you can leave. And actually, we are recording the meeting, and everyone can have access to what you say.
Great, that was great. Okay, so this is the only user ID. This is the only student ID which is not identifiable, meaning that this ID is generated specifically for this data set. This is anonymized ID. So this is the only thing you can use to relate rows to each other. Like these are all the same student. How do you know? Because of this ID, right? Now, practice count means how many times, how many questions this student answered on the practice tool throughout the semester, like from the beginning to the end of the semester. This specific student answered 493 questions. Practice days, how many days of the semester this student used the practice tool? 44 days. So over 44 days, the student answered this many questions. User ID Y is again a repetition of this one. You can ignore this one. Class name, I mean course name, you can also ignore this one, it doesn't matter. Okay, these are important, these are very important, and I have no idea how to, like one of the main challenges we have in this project is how to embed these two in the model. these can play a significant role in our models. These are basically what other previously proposed algorithms for language learning don't have, because in language learning, like, they're dealing with words, and words are not interconnected. So in a college level course, you have chapters and sub-chapters, like sections of each chapter. Questions are related to each other because of these. And these are also related to each other. Like, there is a sequence of chapters and sub-chapters. This is extremely important. We should figure out how to embed this data in our models. So again, this is student. So I told you each row in this data set indicates a specific student answering a specific practice question. So this is saying the practice question that this student answered at this specific time, I mean, the time is here, was from this chapter of the textbook, from this specific section of that chapter. And what was the indicator of the question? This is the ID of the question that a student answered. So there are many cases that you see the student is answering the same question again and again because they answered it wrong. So one of the main important things that we will see here is repetition. That's why, like, in time, over time, they may change their answer to the same question. This is very important. And we have I interval and E factor. So I interval indicates the number of days from now that the system is going to ask this question again from this specific student. So after 12 days, the system is going to ask this question again from that student. E factor means how difficult this was for this specific student over time. You can easily ignore E factor if you like, or if you find any use case for it, let me know. I don't know any use case for it. So these are from my previous algorithm that I've explained these in the, these three are based on the algorithm, the very simple algorithm, like rule-based algorithm that I've used in the paper that I told you need to start with. Now, Q is extremely important. Q is our outcome. If you don't understand Q, you cannot do anything in this project. Q is the correctness of this student's answer to this question at this time. So this is the outcome. So our model should predict Q for each student on each question at each time step. Does this make sense to you? So this is the outcome in our model. -1 means this student postponed this question at this time. They preferred not to answer it, they postponed. The maximum here is 5. 5 means perfectly correct answer. I'm looking for 5 here. Yeah, there is 1 5 here. 4 is correct, but correct answer, but it took some time for the student to answer. 3 is also correct answer, but it took longer time to answer. 2 means it was very difficult for this student to find the correct answer. They spent a lot of time. They tried multiple times, like multiple trials to be able to, like, they had a wrong answer multiple times, and then they tried to find the correct answer. 1 means it was extremely difficult. 0 means they couldn't find the correct answer at the end of the day, right? Like the last submission, like, because they can try each of these questions multiple times before submitting, right? They can receive feedback before submitting their final answer to the question. this is an indication of the correctness of their final answer, considering the number of trials, so how many times they tried to find the correct answer, and the duration, like how much time they spent. And you can find the duration here, like when they started the practice, when they ended. So this student answered this question in 1 second. You see, 1:30. Oh, no, sorry. This is wrong. This should have seconds. Yeah. So Excel shows it in the wrong. Oh, actually, maybe it is correct. Yeah. No, it is wrong. Oh, I have to double click to show you. So they started at 1:39, 30 minutes and 9 seconds p.m. and they ended at 1:31 minutes and 3 seconds p.m. So some seconds are spent on this question, several seconds. So this duration was spent to answer that question by this student at starting at this point, and the outcome was a 4, which is a fairly good grade. And so this is also an important variable. It says how many questions were available for this student at this time to answer, and this student answered one of them. But in total, 11 questions were available for this student to answer. He answered one of them. He may have answered others as well, but at this point, he answered one of them, right? And time zone, if the student travels, the time zone changes. Like during weekends or holidays, they may travel, the time zone changes. But these timestamps are regardless of the time zone. So these are in UTC. So you can just easily use these without time zone. I don't think we will find time zone helpful. And you can ignore next eligible date. Next eligible date is basically based on this I interval that says, like, we want to ask this question again, like, not this question, a similar question on the same topic, because questions are based on topics, based on sub-chapters or sections. It says when to ask another question from the sub-chapter, again, from this student, based on their log of answers, based on that simple formula that I've explained in that ICER paper, in ICER 2019 paper. Any questions? So again, this data set is completely anonymized. The only identification for each student is just an ID, which is randomly generated for each student. And there is no way to figure out who this student is. So it is totally fine to analyze it. Don't share it with others, please. This is only shared within this group. Don't share this data set with anyone else. If someone asks you to share this data with them, any professor or anyone, tell them you don't have the permission to share this data set. Any questions?
Yeah, I don't have questions.
Yeah, I appreciate it, Yua, if you just write as much as you can about the description of these variables in that file. And other people can also join to complete your descriptions in that file. We can collaboratively complete that file. And just let me know if you have any questions on Microsoft Teams. I'm almost always online to answer your questions.
Sure.
So we have a grand vision for submitting a paper to ICML or KDD, but for now, or like SIG IR or something like that. But for now, we want to have a very, very short-term goal to just build a simple model that can have a fair prediction, like fair accuracy of prediction on this data set, and we can submit it to a conference as early as possible.
Okay, that sounds good.
Great.
So Nikki
Sorry
and
for
Nali,
taking your time. What is that?
oh yeah, Nick and Nali, do you have other comments or questions?
Yeah, I don't have any questions right now.
Thank you for your explanation.
Sure. If you don't have any questions, have a good one.
Have a good day.
Bye-bye.
Iman,
Bye.
Iman,
Yeah,
do you have time now?
sure. I'm here for you.
Okay, I will stop the recording.